Assalamu alaikum once again. If you remember the previous lesson, we talked about what? What did we talk about? Of course, we talked about sound intensity, yeah? And of course, we said intensity is basically equal to rate of, let's say, or the time rate of energy divided by, or per unit area, or you can say power divided by the air. And of course, we said intensity is directly proportional with many factors, with the amplitude squared, let's say, with the vibrating area, with the power, and it was inversely proportional with the radius squared, yeah? Very good. And of course, we solved some questions related to that. And we ended up at this point here, we said relative intensity is measured in decibel. Now, what is relative intensity? We also mentioned in the previous lesson that the audibility of, let's say, humans does not depend on frequency only. It depends on both on the frequency and the intensity. In another word, even if you have the right frequency, but the intensity, if it is not, let's say, loud enough or big enough, then more likely the sound is not going to be heard, yeah? Very good. So now today we'll talk about this, which is the continuation, you can say, of the previous ones, and that is relative intensity is measured in decibel. What is relative intensity? Relative intensity is basically, in another word of, let's say, the perceived loudness, that would be, yeah? Very good. So we can say the intensity of a wave is approximately determined by what? By perceived loudness, like how loud the sound is heard or observed, let's say, by the listener. That is basically, we can say, part of the intensity, yeah? And of course, the loudness is not directly proportional to the intensity. Remember this, loudness is not directly proportional to the intensity. It is rather, or you can say, the function between the loudness, or you can say the perception of loudness to the intensity that is more, or you can say it is a logarithmic function. So you can say the loudness is not directly proportional to the intensity. It is rather loudness, it is, like directly proportional to a logarithmic function of the intensity. All right, and of course the function is going to be beta, that is the relative sound intensity, you can say, which is directly proportional to the logarithmic function of I over I naught. We'll talk about this in a second. All right, so do you remember, by the way, we can represent I naught as a threshold of hearing, and of course, that would be a certain intensity of a sound, you can say. So the measure of a loudness is referred to what? Is referred to as a decibel level, you can say. So we want to measure the loudness. You can say this measuring loudness can be referred to as a decibel level. All right, now we have a key term or a definition. What is the definition? That is relative intensity. We can, of course, represent relative intensity by beta. That is a Greek letter, of course. What does this say? It is basically the ratio of the intensity of a given sound, let's say, to the intensity of a sound at a threshold of hearing, okay? And of course, it is unitless. Why is it unitless? I'll tell you this. Okay, let's say, here's the function, of course, you can say. So it is the ratio of what? Of a given, or the intensity of a given sound wave to the intensity at the threshold of hearing. So we can say beta, that is the relative intensity, you can say. It is equal to, of course, we have a function there, which is basically the functions like this 10 logarithmic function of I over I naught. What is this I naught? That is, you can say sound intensity at, sound intensity, all right, sound intensity. Let's go back. Sound intensity at what? At the threshold of hearing. At the threshold of what? Of hearing. And what is the sound intensity at the threshold of hearing? That is about 1 times 10 to the power negative 12 watts per meter squared. So we can say this I, it is always equal to 1 times 10 to the power negative 12, or you can say 10 to the power negative 12. You don't have to say negative 12, yeah? So you don't have to You don't even have to use 1 in this case. And of course, I, that would be the intensity of a sound, let's say at a given, or let's say the sound at a given intensity. Then of course, here is the logarithmic function, you can say. But you do know that the unit of I, it is basically watts per meter squared, yeah? And that is also watts per meter squared. So these two would cancel one another out. So you can see here that the relative intensity or relative sound intensity is a unit less, you can say, or it is unitless. But of course, we do use decibel just to represent this one. So we can say decibel is a dimensionless unit, but it can be used to describe the relative intensity of a sound. So once again, the relative intensity of a sound is a unitless. All right, so, but we use something else to describe how loud something is, and that is decibel. So decibel is not, remember, a unit of, let's say, the sound, or let's say sound intensity, or relative intensity, not sound intensity, relative intensity. It is not a unit of that. It is just a dimensionless unit. We use that to describe the relative intensity. And does that remind you of something when we say dimensionless unit? Does that remind you of anything else that we have covered in Unit 1? It should, I hope. All right. That was radian, yeah? We said it is a unitless or dimensionless unit that we use to represent or to describe the angles. All right, so by the way, so in this case, of course, the relative intensity, we can say beta equals to 10 logarithmic function of I over I naught. Instead of this I naught, we can always use 10 to the power negative 12 because that is the intensity of the sound at threshold of hearing. So I naught represents the intensity of a sound at threshold of hearing, and its value is 1 times 10 to the power negative 12. We've covered this in the previous lesson, so make sure you do know this because there has been a lot of times that they are asking for this number. And you can see here it says the loudest sound. What about the threshold of pain, by the way? Threshold of pain, it was about 1 times 10 to the power 0, yeah? Or we could have just said, I mean, we said just 1 watts per meter squared, yeah? So you can say just 1, that is the intensity of sound at the threshold of pain. So take a look at these questions. The first one says, the loudest sound that human ear can tolerate have an intensity of about. Says, the loudest sound that human ears can tolerate without getting pain, yeah? So what is the loudest sound? We said earlier in the previous lesson that it is about 1 watts per meter square. So which one of these? And that is the correct answer is going to be D. That is the loudest sound. What if the question were, what is the softest sound, you can say? That is going to be the threshold of hearing in this case. And of course, we would have said the intensity would be 1 times 10 to the power negative 12. We have a question like these, you will see, or something. They're asking for this number. Take a look at this. It says the value of I naught. What is I naught? That is the intensity of a sound at the threshold of hearing, and of course that is basically in this equation or logarithmic function. And what is the value of this I naught? It is, we said earlier, it is 1 times, where did I write? It is 1 times 10 to the power negative 12, that is watts per meter squared. Very good. So which one of this? And of course that is A, you can say 1 times 10 to the power negative 12 watts per meter squared. Is it 1? That is threshold of pain, you can say. And this is not that, of course, this is not as well. Okay, remember, it says, what does the I equals to in this equation? That is equal to 1 times 10 to the power negative 12. All right, question 3 says the range of audibility. This is very important. And of course, we did cover this in the previous lesson as well. It says the range of the audibility of the average human depends on what? Does it depend on the frequency only? No, it depends on 2 things. Yeah? We said frequency and the intensity. So let's see if we have this too. Is it only intensity? No. Is it only frequency? No. It is both intensity and frequency, and that is the correct answer here. What about threshold of pain? That is incorrect. So the correct answer is option C. Question 4 says a dimensionless unit that describes the relative intensity. Dimensionless describes relative intensity of sound. That is, what do we said? It says, or we said it is decibel, yeah? And by the way, decibel can be represented by dB, yeah? All right, take a look at these study tips. These are very important as well. All right, what is the first one? It says the threshold of hearing. That is basically, we can say, the minimum sound intensity heard by average human beings. By the way, these are, when we talk about minimum or threshold of pain and all that, we're talking about average, the majority of people. Otherwise, there are some other people which these numbers could be a little bit different too. All right, so threshold of hearing, that is the minimum sound intensity that can be heard by human, which is about 1 times 10 to the power negative 12 watts per meter squared. Very good. What about the threshold of pain? Threshold of pain, that means maximum intensity of a sound that can be heard without getting, let's say, or without pain, all right, or human ear can tolerate, and that is about 1 watts per meter squared. What about minimum relative intensity? By the way, here we're going to prove this. The minimum relative intensity of a sound that can be heard by human, it is 0 decibel. And the maximum relative sound intensity, or you can say intensity level that can be heard by human, it is about, without pain, of course, it is about 120 decibel. And how do we know these? Of course, we're going to prove this, yeah? So take a look. The first one says what? It says, what is the relative intensity of sound at the threshold of what? Of hearing. So we're going to do this. We're going to write the equation that we have. I think this will be enough in this case. Okay. Let's make it white. All right. So what does it say? What is the relative intensity of sound of the threshold at the threshold of hearing? So here's, we're going to write the equation, yeah? So we'll say beta, or relative sound intensity, it is equal to 10 log of, all right, I over I naught. This is always 10 to the power 12, yeah? But the question says, all right, this is the given intensity of sound that you need to know, or basically here's given, yeah? It says at the threshold of what? Threshold of hearing. Threshold of hearing, that means I equals to what? Equals to 1 times 10 to the power negative 12 here. So we can just substitute these two in the equation. So we can say, once again, relative sound intensity, 10, all right, log of, remember, I naught, it is always the threshold of hearing, that is 10 to the power negative 12. And then it says, we want to find the relative sound intensity at threshold of hearing. So of course, if I is threshold of hearing, that means also 10 to the power negative 12. So these two will cancel out. So what are we left? 10, all right, or relative sound intensity, 10 times log of what? Log of 1. And by the way, log of 1 equals to what? Log of 1 equals to 0 in this case. So we can say the relative sound intensity at the threshold of hearing in this case is going to be 0 what? 0 decibel. That's one. Yeah, what if the question were, let's say the second part, what is the relative sound intensity at the threshold of pain in this case, yeah? So we're changing this. Let's say we have a different question, of course. Instead of threshold of hearing, we have threshold of pain in this case. So let's use a different one here. So once again, if I is the threshold, or at an intensity of threshold of pain, that is about 1 watts per meter squared, yeah? So write the equation again, beta equals to 10 log of, all right, I over I naught, all right? So in this case, once again, 10 log of I, that is basically the threshold of pain in this case, which is 1, yeah? And then I naught, it is always 10 to the power negative 12, yeah? You can plug in these numbers into the calculator, or you can do some math before using this, or plugging this into calculator. This goes up, becomes 10 to the power positive 12, yeah? So you can now plug this one into the calculator. Of course, you're going to get, or you can say, log of, this is the base of 10, of course, log of 10 to the power 12, in this case, equals to 12. So of course, the answer is going to be 10. This log of, let's say, the base is 10, of course, 10 to the power 12, that is 12 in this case. So 10 times 12, of course, that is going to be 120, that is decibel. So remember this, the relative sound intensity at the threshold of pain, it is going to be 120 decibel, but at the threshold of hearing, it is going to be 0 decibel. 0 decibel, it doesn't mean there is no sound. It just means that the sound cannot be heard at this level, okay? All right, what if we have something different, let's say? If we have another, let's say, intensity, right? Let's say, take a look at question, or part 3 says, what is the relative intensity if the intensity of a sound is basically 10 to the power negative 3. Let's solve this one as well. All right, let's get it to the side here. All right, so what do we have? We are trying to find the intensity of sound, but where at an intense, or if the sound intensity is 10 to the power negative, oh, not this. All right, let's go back. All right, 10 to the power, I think we have, all right, where did it go? Let me redo this one. So we are trying to find the relative sound intensity. We are trying to find the relative sound intensity if the sound intensity is basically 10 to the power negative, it is negative 3, yeah? So let me see if we can move this. No, not this. All right. What? Yes. All right. So remember this. We have this, yeah? So we'll say relative sound intensity, or relative, let's say intensity equals to 10, right? Log of what? Log of I over I naught. This I naught, it is always, you can say threshold of hearing, that is 1 times 10 to the power negative 12, or you can just use negative 10 to the power negative 12. But then I, that we have here, which is given, that is 10 to the power negative 3, that is watts per meter squared. This is also watts per meter squared. So now all you have to do is just plug in the numbers into the equation. So relative sound intensity, 10 log of what? Log of I, which is in this case 10 to the power negative 3 divided by 10 to the power negative 12, yeah? Of course, you can do some math before you plug in these into the calculator. So 10 log of, if this negative 12 goes up, becomes positive 12. Positive 12 and a negative 3, of course, we're left with 10 to the power negative 9, yes? Okay, so now you can plug this into the calculator. You would get what? And of course, no, my bad, that is positive 9, okay? Because positive 12 and negative 3, it becomes positive 9. So log of 10, you can say this one becomes 9, so in this case, so of course becomes 10 times. You just plug this into the calculator, it gives you 9, so 10 times 9, that is about 90 decibels, all right? Very, very good. All right, what else do we have? It says, take a look. What is the sound intensity? This time, we're kind of like reversing the process. So, we want the sound intensity. In the previous time, we gave you the sound intensity. We were asking for the relative sound intensity, yeah? But this time, we are going to give you the relative sound intensity. We want you to find at what sound intensity the relative intensity would be 90 decibels. So in another word, we would be just reversing the process here. All right, so let's do this again. All right, so so you tell me, what are we going to do? So we're going to find the sound intensity in this case. All right, so what are the information, or what is the information that is given? It says, so we have, says what is the sound intensity? So I equals to 1 if the relative sound intensity is 90 decibel, yeah? And of course you do know that the intensity of sound, or the threshold of hearing, it is 10 to the power negative 12. All right, so knowing all this, now we can say beta, right, or relative sound intensity equal to 10 log of I over what? I over I naught. All right, and of course now you can plug in the numbers, or we can say this is 90 equals to 10 log of what? Log of I over I naught, yeah? So I, we don't know. I naught, you can say that is basically 10 to the power negative 12, but I would rather to keep it this way for now. Okay, so now we do know this. Now these two will cancel out, so we can say 9 equals to log of I over I naught. By the way, the base of this one is this, so if we are dividing this by the base of this 10 over 10, let's say, these are the base, by the way. So in this case, the 9 will become the power of 10 in this case, yeah? And these two now would cancel one another out, so the other side becomes what? Becomes 10 to the power 9. So if I redo this one now, I think it's time to change the color here. So I, right, becomes what? I over I naught, it is equal to 10 to the power 9. All right, now we can cross multiply, yes? So I equals to 10 to the power 9 times 10 to the power, or I naught, yes? So I naught, we do know that I naught equals to what? Negative or positive 9, my bad, right? I naught is 10 to the power negative 12, yeah? So negative 12 and negative 9, that is basically 10 to the power negative 3. Negative 3 what? That is basically watts per meter squared. So take a look. What did we do here so far? We have the relative sound intensity. We found the intensity of sound, let's say there. So you write the equation, try to cancel out this two. You're left with this, yeah? Then take the base for both the logarithm function and then the other side. This becomes 10 to the power 9. This 10 with log will cancel out, so we're left with I over I naught. Now cross multiply. Once you cross multiply, of course, I equals to 10 to the power 9 times I naught. But you do know that I naught equals to 10 to the power negative 12. Then do some math, you will end up with I equals to, or the intensity of sound at 90 decibel equals to 10 to the power negative 3. And of course, there are some fast ways you can do that as well. And the fast way is if you're going to change intensity of sound to relative sound, then of course you can say 12, right, plus the power of 10 multiplied by 10. Like one example for that, for example, basically we have, let's say, if I is the relative sound intensity, we have the relative sound intensity, let's use blue, relative sound intensity, the intensity of sound is 10 to the power negative 5, yeah? So using this fast way, that is going to be 12, right? If you want to find the relative sound intensity, we'll say 12 plus, this is negative 5, yeah? Then 12 and negative 5, that is what? That is basically, becomes what? Becomes 7. So 7 times 10, that is going to be 70 decibel, yeah? What if we do the reverse? What if we have, let's say, sound intensity, relative sound intensity, and then we want to find the intensity of a sound? Of course, we can say I equals to 10 to the power, the relative sound intensity divided by 10 minus 12. One example for that, if we have 80 decibel, we'll say I equals to 10 to the power 80 decibel divided by what? 10 minus 12. So 80 divided by 10, that is 8. Yes, 8 minus 12, that is going to be negative 4. So the intensity is going to be negative 10 to the power negative 4 watts per meter squared. By the way, I would rather you do the upper ways. These are faster ways. Sometimes these are very good if you don't have enough time. But if you do have enough time, always take the other one, which is way safer, because sometimes you might get confused. You might not remember this precisely. All right, now we have a study tip. Remember, it says the change in the relative sound intensity by the level of the noise can be represented as follows. Let's say, right, let's say, for example, you are at a place, yeah? So the sound or the relative sound intensity will change, let's say, from something to something else. Let's say it changes from 20 decibels, let's say, to 30 decibels, from, let's say, 80 decibels to 90 decibels, yeah? So what will happen, or how do you represent that? And of course, when sound or relative intensity changes, we can say delta beta, yeah? Or delta relative intensity, which equals to relative intensity, the second one, or final minus the initial, yeah? Or 2 minus 1. And of course, the equation is basically 10 log of always intensity of a sound, let's say intensity of a sound divided by the intensity of sound 2, of course, divided by intensity of sound 1 here. So, and of course, you plug in the numbers and you just do the math and you will find the answer, whatever the answer is. So take a look. We have a question similar to that. What does it say? It says, when the level or when the decibel level of a traffic in a street goes from 30 decibel to 60 decibel, yeah, how much greater is the intensity of the noise, or how much the noise will be greater, yeah? So in order to answer questions like this, because we have 2 decibels, yeah? So remember, we're going to use the equation that we just said. We'll say delta B, all right, equals to B2 minus B1, yeah? And of course, this one equal to 10 log of, remember this, I2, all right, over I1 here. All right, so in this case, now you have to plug in the numbers. So we have 60, right, minus 30 equals to 10. And of course, we have log of I2 over I1. Now, of course, 60 minus 30, that is 30, yeah? And then equals to 10 log of I2 over I1. And of course, now these two can cancel out as well. So we can say, let me write it here. So we can say 3 log of what? Log of I2 over I1. Now remember this, we take the base for both sides. So in this case, it's going to be 10 and 10. So it becomes 10 to the power 3. The other side, these two will cancel out, becomes I2 over I1. Now you can cross multiply, yes? So we can say I2 here equals to 10 to the power 3 I1. In another word, I2, or the level of the noise, is going to be 1,000 times the level of the noise when it was just 30 decibels. So remember, this is how it is done. There is another way which I'm going to tell you. The second way is this. Remember, when the decibel increases by 10, right, you can say the intensity will be multiplied by a factor of 10. So remember, the intensity or the decibel increases from 30, right, to 60. So from 30 becomes 40. You can say from 30 to 60, yeah? So that is going to be from 30 to 40, and then you can say from 40 to 50, and of course from 50 to 60 as well, yeah? So how many times does it increase? That is 1, that is 2, you can say, that is 3 as well. So every time the intensity increases, let's say, or the decibel increases by 10, the intensity increases by 10. So that is going to be 10 times 10, that is times 10 as well. So it is going to be increased by 1,000 times here. All right, we'll emphasize on this a little bit more in the previous, in the upcoming questions, inshallah. Take a look at this one. It says when the decibel level of a traffic on a street goes from 40 to 60, yeah, how much greater is the intensity of the noise? You will need to use or do the same calculation that I just did, or there is another way as well. It says from 40 to 60, yeah? So from 40, let's erase this. From 40 becomes what? From 40 we can say becomes 50, yeah? Then from 50 becomes 60. So every time the decibel goes up by 10, you can say the intensity will be multiplied by 10, all right? So from 40 to 50, that is multiplied by 10, all right? And then from 50 to 60, that is again multiplied by 10. So in this case, you can say the level of the noise will be increased by what? By 100 times, or you can say by 10 to the power 2. That is also possible, yeah? So when the decibel levels of the traffic in a street goes from 40 to 60, how much greater is the intensity of the noise? And of course, it's going to be B, which is 100 times. If not, if you don't want to do this, of course, you can do the calculations that I just did. Then, of course, you will get to the correct or to the same answer here. Now, we have another study tips. It says to find the number of machines, use the following, yeah? Normally, or you will see that in the coming questions here, they are asking us to find the number of machines, let's say in a factory or in somewhere. So in this case, if they want to, if they are asking you to find the number of machines, in this case, we can always use I2 over I1 as we can represent that as n, and n represents the number of all the machines, or you can say the total numbers or the total number of the machines here. Okay, so for example, we have a question, right? We're going to solve. Just bear with me here and let's solve this question. What does it say? It says a noisy machine. So how many machines do we or are we talking about here? A noisy machine, yeah? So we have one machine that is noisy. Okay, so a noisy machine. All right, let's get this one done. All right, now we can move it up a little bit. Okay, or you can keep this one, it doesn't matter. All right, so it says a noisy machine in a factory produces a decibel rating of 80 decibels, yeah? How many identical machines could he add to the factory without exceeding the 90 decibel limit set by the federal regulation? So in this case, of course, remember the equation we just had, yeah? We said if we have to, let's say, relative sound intensity, let's say level, of course, we can say delta B equals to what? B2 minus B1, which equals to 10 of log of, let's say 10, all right, that is 10 log of, previously we said, of course, I2 over I1, yeah? But now we're going to use what? We're going to use N instead. So we can say this one, N. What does N represent? N represents the total what? Number, right, of machines, you can say. Total number of machines. All right, so now let's do the math, yeah? So we don't want to exceed 90, so of course 90 decibel minus 80 decibel equals to 10 log of n, yeah? And of course this one equals to 10, right? Equals to 90 minus 80, that is 10, equals to 10 log of n. And of course now you can simplify this to, that is basically 1 equals to log of n, yeah? Now take the base of both these two together for this. So these two will cancel out here. So 10 to the power 1. What is 10 to the power, what is left at the other side here? We can say 10 to the power 1 equals to n. But what is 10 to the power 1? Isn't that 10? Yeah, so we can say n is equal to 10. But 10 what? 10 machines. But that is not the answer to our question. The question says, how many identical machines could you add? Yeah, so how many machines do we have? We have one machine, yeah? So the total machines that we can have it is 10. So we have one machine. So of course you can say 10 minus 1, 9. So we can add 9 more identical machines so that we can have 90 decibels or without exceeding 90 decibels. So once again, this n represents the total number of machines. So the total number of machines that we can have is 10, but we already have one machine. So how many more machines can we add? That is 9 more machines we can add so that we can have a total of 10 machines. All right, this is something very similar to that. All right, now we have another question which is very important. It's been in the exam many times, yeah? It says, a baseball coach shouts loudly at an umpire standing 5 meters away. So what is the distance? That is 5 meters, okay? So we can say this is R, which is basically 5 meters. If the power or if the sound power produced by the coach, so we have power, right? This is power. What is the decibel level, the sound of the sound when it reaches the umpire, all right? So now we're going to find what? Find the decibel level. All right, so how do we approach this one? All right, take a look. The first one, in order to find the, or what does the decibel level equals to here? Or sound, let's say intensity. Give me a second. All right, or relative sound intensity. So we do know that B or so relative sound intensity equal to 10 log of what? Log of I over I naught, yeah? We're trying to find the what? It says, what is the decibel level? That is basically relative sound intensity. That is basically another name for that is going to be decibel level, yeah? Very good. So in order to do that, of course, 10 log of this, we do know this one, yeah? But do we have the intensity of a sound when it reaches the umpire? The answer is no. But how do we find the intensity? We do know that in order to find intensity, because power and radius are given, so we can say intensity equals to power over 4 pi r squared. What is the power? That is 3.1 times 10 to the power negative 3, yeah? Divided by 4 pi r squared. What is the r? R is 5, so in this case it's going to be 5 meters squared. So what is the answer to this? Let me get a calculator. Okay. So remember, 3.1 times 10 to the power negative 3 times 10 to the power negative 3 divided by what? Divided by 4 pi times r squared, which is 5 squared in this case. The radius is in meters, so you don't have, or r, the distance is in, so you don't have to worry about this. So of course the answer is going to be, or the intensity is going to be, let's convert this one to scientific notation. All right. So the answer, or the intensity, is going to be 9.87 times 10 to the power negative 6. That is the intensity, watts, of course, per meter squared. Now, of course, we can plug in this intensity into the equation, then we can find that. All right, so now B equals to 10 log of, all right, the intensity that we have, that is, what is it? That is 9.87 times 10 to the power negative 6, and then divided by, this is the threshold of hearing, yeah? What is it? That is 10 to the power negative 12, always, yeah? All right, so now, once again, you can plug in this number into the equation, and of course, it will give you a number. Then 10 multiplied by this, let's do this one too. So of course, we have log of 9.87 times 10 to the power negative 6 here. Negative 6, all right, divided by what? Divided by, let's go back to this. All right, and then divided by 10 to the power negative 12. Now we can close brackets. So of course it gives us what? It gives us 6.99, which is about 7 in this case, yeah? So of course we can say 7. So 10 times 7 equals to what? Equals to 70 decibels. So we can say the relative sound intensity, right, or the decibel level when it reaches the Umpire, of course, is about 70 decibel. So what did we do in this question? Remember this, they were asking for the decibel level, right? But we did not have the sound intensity, but instead they were giving us power and the distance or the radius here. So of course we're using the power and the radius, we found the intensity, then you plug it into the equation, then you can find the decibel level or the sound intensity, or you can say relative sound intensity. All right, now, question 14 in chapter review says, what is the difference between intensity and decibel level? Can you tell us the difference? Of course, in this case, you can tell me their definition. That'll be the best definition or the best difference between the two. Wave intensity, all right, that is basically power per unit area. We did talk about this, yeah? Or sound intensity, you can say, power per unit area. Very simple. What about decibel level? Describes the relative intensity of a sound, or basically the perceived loudness, you can say, yeah? All right, so once again, sound or wave intensity, that is power per unit area, while decibel level, or you can say decibel, it describes what? A relative intensity of sound. All right, then conceptual challenge, that is not included, or you can say cancel. All right, I think we don't have enough time, but I'll give you an idea about forced vibration and resonance as well. Now, what is natural frequency of a system? So take a look. Let's say we have different, or if we have something like this, let's say we have different pendulums. Each one of these you can see here, 3 of them are in different length, but of course you can see here, these 2 have the same length, and and of course you can see here, these are, or the strings are attached as with an elastic band or with a band, of course, so that when you vibrate one of them, of course, the vibration, or because of the effect of this vibration, the others can vibrate as well. But of course, we do know that let's say, if we disregard this blue one here, we would have 3 different pendulums. Each one of these 3 pendulums, when you give them, let's say, a specific, or let's say a certain amount of force, let's say, to make them vibrate, each one of these would vibrate, let's say, differently, yeah? Or you can say each one of these would have a different or a certain vibration which is different from the others. Why? Because they have different length, yeah? Do you remember, like the period, and so the frequency of a pendulum, we said period, of course, equal to 2 pi square root of length over the or gravitational acceleration, let's say, or free fall acceleration, you can say. But then if you want to find the frequency, that is going to be 1 over the period, or you can say frequency equal to 1 over 2 pi multiplied by the square root of what? Of free fall acceleration divided by the length. So of course, different length causes or makes these pendulums to vibrate with different frequency. So vibrating with a different frequency, that is basically what is called natural frequency. So what is natural frequency? It is the rate at which a pendulum oscillates when left undisturbed, like the swinging of a pendulum or the vibration of a guitar string. So let's say you just pluck it once, and let's say we have, for a guitar string, of course we have different strings, yeah? When you pluck, let's say, each strings with the same force, let's say, yeah? Do all these strings sound the same? The answer is no. They sound different. The reason why they sound different is, one of the reasons you can say is because they vibrate with a different frequency, or you can say each one of these would have a different frequency, yeah? Or vibrate differently, let's say. So of course, this different vibration is, you can call it natural frequency. It is the frequency that it vibrates with when it is left undisturbed. When you don't, let's say, stop the vibration, it just vibrates on its own, let's say after giving it a push, and it swings back and forth or just vibrates. But remember, if it is undisturbed, yeah, like these examples. But we have something else called forced vibration. What is forced vibration? Forced vibration is basically, it is the oscillatory motion of a system caused by an external force. What does that mean? That means, for example, let's say we have a guitar string, yes? Now you just plug the string, the body of the guitar vibrates with what? With the string. That is called forced vibration. You didn't plug the body of the guitar, yeah? But because of the vibration of the string, now the body of the guitar is vibrating with it. So now the body of the guitar is forced to vibrate with the string, and that is called forced vibration. So it is the oscillatory motion, the vibration of a system, let's say, that is caused by an external force. All right, so of course we have an example or a situation. Take a look. It says, consider a set of pendulums suspended from a beam and bound by a loose rubber band as shown in this figure here. If one of the pendulum is set in motion, let's say one of the blue one, the vibrations are transferred to the rubber band, let's say to the other pendulums, which will also begin vibrating. So if you just make one of them vibrate, you can see that all the other pendulums will start to vibrate because of the vibration will be transferred to this loose rubber band, and of course then it will be transferred to the pendulum, then all the other pendulums will start to vibrate, yeah? So, and which will also begin, or you can say other pendulums will begin vibrating. This, or when the other pendulums start to vibrate, that is basically called forced vibration, all right? So remember this, natural, or you can say natural frequency, it is, let's say, the vibration of an object when it's not disturbed by other pendulums, by other forces, by other vibrations, yeah? All right, you just plug it once, or you just, let's say, if it is a pendulum, you give it one push, it swings back and forth, it vibrates, yeah? If it is not tied to any other stuff, let's say. But we have something else, it's called sympathetic vibration. What is sympathetic vibration? Of course, that is when one object starts vibrating because of the vibration of, or you can say from other nearly objects. Just like one of the pendulums, yeah? You just make or give one push to one of the pendulums, then the other pendulums start to vibrate because of, let's say, the rubber band, or you can say this vibration is transferred to the rubber band, then to the other pendulums, then other pendulums start to vibrate with it, yeah? But of course, there's something else you need to know later on. We'll talk about it, yeah? When these vibrate, because these two have the same, or these two have the same length, that means they have the same frequency. So we'll talk about this one in more detail in the next lesson, inshallah. But it says when this one, or because these two have the same frequency, so it is true that all the other pendulums will start to vibrate, but the one with the same frequency or the same length will vibrate with the maximum amplitude, you can say. So take a look. Let me go through this one for now as well. What happens when the string of a guitar is plucked? This is something you need to know. The vibration of the string of a guitar forces the bridge, yeah? So imagine the shape of a guitar, yeah? You have, so the string will transfer the vibration to the bridge of the guitar that is attached to the body of the guitar, yeah? So you can see here, which you can say bridge in turn transfers the vibration to what? To the guitar body. And of course, these forced vibrations are called what? Sympathetic vibration, because the guitar body has a larger area. Do you remember previously we talked about intensity? So this guitar vibration or string vibration is transferred to the whole, or to the body of the guitar. Now the whole body of the guitar is going to vibrate, so it sounds louder, or the intensity gets louder, all right? But remember, the vibration of the string will die out faster because the energy of the string is transferred to the body of the guitar more efficiently. So the vibration dies out faster, but it sounds louder. Okay, So you can see here, or the bottom of this, it would be the guitar body allows the energy exchange between the string and the air to happen more efficiently, thereby increasing the intensity of the sound produced. All right, now that is, take a look. Question 25 is related to this. Why does the vibration of the string sounds louder when it is on an instrument than it does when it is stretched on a workbench, let's say? So if it is just a string, it doesn't sound that loud. But if it is attached to the guitar body, of course it sounds louder. Why? That is because the vibrations are transferred to the instrument's hollow body. The body, the whole body, you can say, of the guitar, if not the whole, at least the hollow body would vibrate in a much larger volume of air, creating a louder sound, of course, higher intensity, you can say, and of course, increasing the intensity of the sound that is produced. Or you can say, we have a study tip, we can say the bigger the body that vibrates, the more the intensity, and of course, the louder the sound. Next time, inshallah, we'll start with vibration at natural frequency produces what? Produces resonance. So that is it for today, or for this session. Make sure you review, or go through this one more time. Make sure you practice the questions that we had, so that you can master all this. If there is anything that you left, let's say, not mastered, you can master these concepts, right? Till next time, make sure you practice, and I'll see you next time. Have a wonderful day. Assalamu alaikum wa rahmatullahi wa barakatuh.